Okay, go ahead.
Right. So I started making a presentation in slides in Overleaf, but there are like 3 videos I want to show, and I was having difficulty putting them there because it's not a video format. But meanwhile, my notes in this note system here called Obsidian were looking pretty nice, and I have all the videos in line. So I said, you know what, this is my presentation. So I'm just gonna go with this. Right. So I wanted to give a brief overview of physical learning because I don't know if everyone watching this knows what physical learning actually is, but it's where you study systems in physics that display learning behavior. This is a very intuitive hand-wavy explanation, but kind of like neural networks, but in real life, like real system where the equivalent of a propagation, where you do calculation by hand, is actually done by physics itself by minimizing energy when you manipulate things in a certain way, right? So this is a very general definition of it. The paper actually uses a little more restrictive definition. It centers around materials. So like in this context of materials, physical learning would be something more like a set of springs or maybe a sponge where when you press on top of it, it might bulge on the sides. But then if you train it by pressing on the sides and the sides as well, then it's going to weaken some of the fibers of the sponge. So next time you press it on top, it's not going to bulge to the sides. That's a very simplified learning physical system, but that's the basic idea. And in this context, previous works focused on static properties, like the one I just described about the elastic response of a sponge, for example, self-assembled structures and stuff like that. And usually they correspond to like a minimum in the energy landscape. And this paper, they're actually trying to describe a more general dynamical set of solutions you can get, right? Instead of just change the elasticity or change how it behaves in a certain way, it moves. It's going to be a time-dependent thing. Well, it comes down to 2 ingredients with learning rules with time delays and training examples that break time reversal symmetry. And we're going to go through 3 examples, models that do that illustrate that. So the first one is a toy model, and a very literal toy model because they use Lego motors to model the system. But under the hood, it's actually an XY spin model with just 2 spins. That's what it is. It's a very simple model. We have 2 angles, theta 1 and 2, and they behave according to this equation that defines the model. So we have this JIJ, which is the coupling that tells how the angle J influences the angle I. And then we have a training rule, right? The training rule is the equation that tells us how the thing
Diego,
that we
can
want
you
to
zoom in? Is it possible to like?
Oh yeah, I'm pretty sure I can.
There's a lot of. If you don't know, that's fine because there's a lot of black space on the sides. That's kind of not.
Yeah, that's not. That was not ideal. I should probably have stuck with
No,
the.
that's fine. Okay, forget about it. Sorry. Go ahead. That's not. Don't worry about it.
There we go.
There you go. Okay.
So yeah, so the learning rule is basically the dynamic equation that defines how the couplings are going to change, right? So the couplings are the things that we want to change about the system, what we want to train. So that this equation basically tells us how that works. And in this case, they have this term here, this integral, which looks a lot like a path integral, goes from minus infinity to time. And this is an interesting aspect of the insight of this paper, that if you introduce the time delay, the learning rule, then you can actually have that's the first step. But let's look at this integral a little closer. Like we have this this g here is down here we can see it's exponential minus tau over tau 0. This is the time delay, right? So when you're training the system and you're going to do the time reversal training, you need something like this in order for that to have any effect. Right, so this basically introduces they call it a memory kernel because it means that the training takes into account the entire history of the system before. Right. So yeah, you have CS. Okay, yeah, no, that's what I just said. So you need the time delay in the learning rule in order to have a time reversal training. We're going to look at the video that is going to explain a little better. So the first part of the video, he's going to, this is all using the same learning rule, right? He's not going to change the learning rule. He's just going to change the training. In this first part, he's doing a training that is time reversal. That is, if I play this video backwards, then it would look identical. You can see the progress of the coupling constants on the graph there. Right, so no time reversal in the training, even with the time delay in the training rule, learning rule. So this is the end result, right? So
the evolution for coupling constants there are coded. So they're still computed.
They're coded. Yeah,
right.
it's completely artificial. It's just coded.
Okay,
yeah.
Sure.
So this part you can see that it's one angle is just imitating the other, just gets the other angle. It's not dynamic. Now he's going to train it using a time irreversible pattern. Like they have different speeds and they accelerate and it's not, if I play this video backwards, it would not look the same at all. Then what happens when you execute it with this new learning rule? Then it gets stuck into this chasing dynamic, right? And this is what they call this is the thing that they are exploring in this paper, right? This kind of solutions that are more dynamic, kind of fixed. So next model they use is a particle-based model, which I thought initially it was more like a fluid system. I never saw this. This is a equation that governs the system, right? Thank you. I never saw this before. It looks very contrived to me, but apparently it was introduced to model some more complex. Here's the definition of the original model. This is a simplification of it, but it's a predator-prey interactions between droplets driven by non-reciprocal oil exchange. So it is a contrived example, but it's something that displays some kind of chasing behavior, right? It's also used to model like white blood cells that chase down and eat bacteria and other kinds of molecular interactions that are similar to that. But fine, so this is the equation that governs it. So we have a concentration, the Ci, then we have the tau, which is like the chemical that it emits. It has a radius, and the decay lambda. So basically, like each particle is going to have like an area of influence that's going to tell other particles how to respond to it. That's the basic idea.
So, but it's nothing but like Fokker-Planck equation, I think.
The what equation?
Fokker-Planck diffusion equation plus the source term. I mean,
it might actually be, yeah.
Because C is a concentration, so it's like probability density. And then
I didn't recognize the different letters.
We have Fokker-Planck for each of the species. I don't know, and then there is.
In this case, they have side functions. So it's
and then there is a coupling between them, right?
The coupling is going to show up here. So this is the dynamical equation for each particle, right? How it's going to change. And this n, the direction is going to move is where we're going to have the parameters that we are going to change, the Wij's. This is the chemotactic mobility. I talked about chemotactic here. It's the thing that makes it chase other things. Basically. So this is what we want to change. So basically, we want to train the systems to change where the particles are going to go. Right? These are the things. So the learning rule. The learning rule is going to again have the same. It's not immediately obvious here in the first form of the equation, but it can be rewritten in a way that we get again the time integral, the path integral, with the propagator G there. Again, it's a memory kernel. It has a past knowledge of the system, and it has Do we have a tau in this one, or it's hidden somewhere? It's hidden. Fine, but yeah. So it's a learning rule, and it has a time delay imbued in this memory kernel. So they showed the derivation for the particle moving at constant velocity just to get a better picture of what's happening. And at constant velocity, we see the concentration gets this comet tail. And this asymmetry is important because it's basically what tells one particle knows if the particle is at the front of it, if it just passed, or if it's passing through, or it gives a lot of information just with this simple asymmetry. So with that. So let's take a look at the video here because it shows the sorry. Right, so we have a learning rule with a time delay inside the path integral. And this is time irreversible because it's spinning in one direction, right? To play the video backwards, it would be different. So it's basically teaching to chase another particle. And this is how they function in practice. When they start spinning in circle, that's the dynamic
Fixed point.
yeah. They don't call it fixed point. It's confusing, but they use fixed point literally, like it's fixed. So this they call this a limit cycle or something like that.
Well, it's not a fixed point because it's dynamic. Yeah, it's limit cycle. Yeah.
Yeah.
Sure.
And this is the another pattern that they showed, which can be used to like model maybe self-assembly things, or just like again a white blood cell eating a material or something. Yeah, so these solutions are possible with the time delay and the time irreversible training pattern. Oh, we have another video for this. Right, so they train with time reversal symmetric. So the particles they never reach limit cycle result. They just move towards each other and stop. Station. And this with the training protocol that breaks time reversal invariance, and now the system can enter these dynamic states.
So can I ask you a question? So I mean, I understand that the particle go to some kind of cycle, fixed cycle, whatever it is, but the interaction had been learned. So like if you pull them apart, the particles, they will not follow the same trajectories, right? Because something in their interactions had changed. I'm just trying to isolate those two types of dynamics. One that has to do with learning, interaction, and the other one that has to do with the activation dynamics, and like not put everything together.
Yeah, I'm pretty sure that you can probably, even with a time irreversibly trained system, you can still put it in a fixed position depending on how you start the system, right? I don't know if the opposite is true, like if you could actually put the system into a dynamic state if you don't have a time delay and all that kind of stuff. I don't know if that would happen.
No, I mean by hand, just change your initial state. You learn interactions like in a spin model, and then or in this particle model, and then start with different positions and see how it will behaves differently because now interactions are different. Are they doing that? I'm trying to separate those two scales, two types of dynamics. One is
the learning
what the particles do once they learned, and how the learning takes place.
Yeah, they are not that different. They separate. Actually, they do mention this at the end of the paper, like the separation between training and
Activation.
Activation, I guess is artificial. They separate it and then they stop training afterwards. But they even mentioned that you can actually have a system that continues learning all the time, even though it might have like problems. You can actually learn something wrong you don't want to, or something like that.
Sure, but I mean,
but the separation is artificial. Yeah, that's I think that's what you're saying, right?
No, I'm saying that you would in any physical system you if you wanted to do learning and activation, you have to have those two time scales present, and then
Right. Yeah.
I'm interested to see what actually sets those scales, how you can separate the scales. Ideally, that's what you want. You want to separate the scales. I mean, now the system is
Uh-huh.
learning. Now I want to this learning, and it stopped learning, so I want to make the learning time scale send it to infinity, and keep on,
Yeah.
on the activation time
Yeah.
scales.
I can tell that they are separating it. Like this is very obvious in this part video that I showed, but I don't know exactly how if they're changing
Like let's
what
say the
exactly is going
temperature,
on
for
under the
example.
hood exactly.
Yeah,
What?
so you change temperature, and then all of a sudden the learning time scales goes to infinity, or something like that.
Yeah,
Okay,
I
fine. So they're
don't know
not talking
exactly what
about
that is.
this.
No, not directly. They do mention it at the end of the paper. Like you can have both running at the same time. They do mention it, but they don't elaborate much on it.
No, but that's the problem. If you have both of them running at the same time, the whole thing is like you don't want the system to unlearn what it has already
Oh,
learned.
right. No, you can, but they're not. I'm pretty sure they're not doing that
Okay.
here. Like I think they're just separate. Like this is training, and it's just reading the results, and then now it's not learning. They're not updating the constants anymore.
Well, that's artificial. Here
It
you
is
just,
artificial.
yeah, what I'm thinking like more in physical model, how you can send those to separate the scales.
Yeah, that's a good question. I don't know. I think that's a problem they did not tackle, but it is interesting. Well, right. We just saw this video, right? Yeah. So the Hopfield model. This is the last part of the paper. The only reason they used this model because they wanted to have a more analytical result, something that they could like uh, have an exact equation that they can study. There are no funny videos, but the Hopfield model, to me at least, is very new. I never heard of it. I know it's a spin system. I just put the Wikipedia summary here, but it's basically, it was introduced in the 80s. There's some kind of like a memory kind of system that can learn things. Seems very ahead of its time. But anyway, it is a spin system. Here we have the equation defining it. Like the easy model, we have like a couplings, but they can there's also this other term that breaks symmetry. It's the cube of the spin with some constant. But fine, we do have a learning rule, and again we have the learning rule with a time delay. But this time they also introduced the sigma, which is a parameterization of the asymmetry, right? So if it's one, it's completely asymmetric. That's the point. And yeah, they do the whole derivation and they come with the exact solutions. These are the fixed solutions, right? So no movement, fixed, no dependence on time. And we have this dynamic solution for the spinning, cosine and sine. But the interesting thing is that they actually write a condition that separates these two solutions. So we can actually look at the phase space and see how that behaves, how it works. So the blue areas here are the fixed points where they eventually evolve in stop, and the red ones are where they get stuck in some kind of cyclical behavior. So yeah, they show that these regions, they change as we change time delay, which we saw before as being important, and also as symmetry, which was not initially obvious, but the asymmetry of the system is also important. And to stop the spins, it has to be, it behaves differently. Right. So yeah, that's the whole paper. I have some additional notes that I was going to address. This is what you mentioned. We're having like what happens when learning continues during pre-evolution.
No, but even
And
in this last model, like if you work, there are two equations. There's one for S for the spins and one for J's for the coupling. So it's if you go, those are solutions, right? So
yeah,
you see here there are two equations. One is for activation dynamics. So if you fix J's,
yeah. How
then
are we going to evolve both of them?
yeah, spins go someplace, right?
Yeah.
periodic or not, that doesn't matter. I mean, it depends. But and that's your solution for the activation dynamics. And then they have learning dynamics. So basically, by adjusting this alpha and kappa, you can make J to change slower than S, and then presumably you can also
Yeah,
send alpha and kappa to zero by doing something with your physical system so that this learning stops, and then other way around, send it to be large, and then learning proceeds. So that I kind of seeing a physical system where you can actually do that, and also modify the both equations, not just having this cubic equations, but having something more complex would be uh, like learning. So I mean, and then the modification, the dynamics for J would be like modifying your loss function, and modification dynamics for S would be like modifying your activation function. So that would be interesting to see how you can do it. Um, what are the tuning things? What
mhm.
things you can tune in the actual physical system, spin system? Um, so they haven't talked about that, right?
No. Mm.
Okay, good. And for those spin model, is those SIs like plus or minus? Are they what is the model? What are the SIs? Are they're continuous variables or discrete?
These are
They're
continuous
continuous.
variables, yes.
Okay. All right. Perfect.
Uh,
See any questions? Any? So are they like referring to any experimental or like
I,
actually picking
no,
up a system that does that? Or
not really, no. No.
so they're still hypothetical.
It's all very artificial for now, just
Mhm.
looking at what does what. I
Sure.
think going to physical is a big step, really.
Well, that's what needed. Absolutely. Okay. So any questions? I think Dan
Uh,
has a question. He
Not a
always has
question
a
so much
question.
as an observation. So yeah, the going to physical, if equation 9, for instance, on the screen were describing a particular physical system, those VIJs would be the ones that describe those systems, that system. So here where they're doing their training, and they go to, as was presented, a slightly more complicated one that has a coupling that has the time dependence. You know, you are able to exhibit or interrogate the behavior of a system with those parameters. So you don't necessarily need a machine learning sort of model to train those couplings, but I really like what they did here, because you could take observed behavior, say, as was described, cells in a cells in a bloodstream or droplets on a slide. You can take observed behavior and use that to determine what your coupling coefficients must be for this particular system.
Mm.
Mm.
And that
So
gets you to now you can make predictions about what would happen with this same system in a different initial condition.
I see. So maybe you're saying that you just look at what the system learned and then, well, use it for
Look
what
at
it
what the
learned.
system did in
Mhm.
order to determine why the system did it.
Oh
Right.
When
yeah,
I was
yes.
looking at droplets on a substrate and what they were doing, gosh, yeah, there were parameters in our models, and we would use the experimental data, the observations, to determine what those coefficients, what those parameters must have been, assuming the
Mhm.
model is correct, what those coefficients must have been in order to cause the observed behavior, which then allows us to make predictions for what's going to happen in future slightly different scenarios.
Right.
So that
Yeah,
might be the route to utilizing this and or getting it to describe physical systems.
Right.
it's interesting. Yeah.
Absolutely, but I mean, I think there's you're still going to have two types of equations, and I don't think I'm saying something new or something that disagrees with Dan, but there would be an equation for those coupling constants, and that would kind of correspond to learning dynamics, and there would be equations for the spins that would correspond to activation dynamics. And so, this system will be useless unless you can separate those two scales. Because what will happen is, you learn something and then it will unlearn it very fast. And so you don't want that to happen. You want to have like tuning, something to tune. And okay, now you learn, like raise the temperature, you learn, like lower the temperature, stop learning, something like that.
And this may also be useful as you, I'm going to say reverse engineer those parameters as you train, which will determine those parameters from the observational data. Well, that can help you build your ab initio models for what those couplings should be or would be in those situations.
Sure. Oh, another interesting point, it's like you may not have all of the ability to tune what the effective loss function is, but just take a material, observe what it learned, and then see what kind of problems this kind of material can solve. Like, yes, you won't be able to freely choose whatever loss function you want, but kind of just look at what it does and then figure out what kind of problems it would be capable, learning problems it would be capable of solving. This may also be possible. Okay, other questions, comments? Well, no, thank you. Diego, thanks everyone for coming. And I'll see you next week.
Thank you.
All right.